Okay, this is an instrumentation amplifier. And the first thing we're going to do is we're going to look at a generic instrumentation amplifier. And what I mean by that is that our generic one, um, I can have different values for R3 and R4. But notice that R3 and R4 here, this R3 and this R3 match up, and this R4 and this R4 match up. Our R4 is our feedback resistor, and R3 is our input resistor. But notice that here I've got R2 and R2. So this is a typical um, standard or generic instrumentation amplifier. And what it provides is if we have R4 over R3, that gives us some additional amplification. Um, so I'm just going to write down the equation for V out with this configuration. So I'm just going to delete some of my uh, highlighting there. So I want you to know that V out for the generic example is 1 plus 2R2 over our gain. And so that is, this is my R2 here, and this R2 here, and this is my gain. So those are the resistors we're talking about. And then this is going to be R4 times R4 over R3. So those are these resistors. And then we're going to have times V2 minus V1. So those are my inputs on the left-hand side here, V2 and V1. Okay, so what we're going to do today is we're going to simplify this, and we're going to change all of our R2s, R3s, and R4s into just R. So I'm going to go over here, and I'm going to just delete these values. So I'm going to have R's for all of them. And let's see how that changes our equation here. So I have V out then. V out is going to equal, oh, I forgot this was a 1. Okay, well, 1 plus 2R over RG, and then R over R, because R4 and R3 are now both equal to R, times V2 minus V1. And so this gets canceled out. And so I'm just left with V out is equal to 1 plus 2R over RG times V2 minus V1. So we'll use that later on when we're going to do our calculation. And we could even do it now. So let's just do that. We'll just plug in. So V out then is equal to 1 plus 2 times, our R is 6,000. So 6K divided by RG is 3K. Okay, times V2, so let me go back, times 4.2 volts minus 1.9 volts. And notice that this right here is 12 volts, right? So this gives me, I'm going to have 1 plus 12 over 3 is 4, times 4.2 minus 1.9 is 2.3. And when I do that multiplication, I'm going to get V out. So V out is equal to 11.5. So that's our V out. Let's see if I can get rid of this. 6K. There we go. Okay, so now we want to go back and we want to also do this problem by working through all of the currents and the voltage drops. So one thing to notice right here is notice that at this location, right, because I have an op amp with negative feedback, and notice I have negative feedback because I'm looping this back around, right? And so this resistor is the feedback resistor for this op amp. And the same thing here, I've got this V1 is the same, V1 is going into the non-inverting input, and that's the same as my V minus, right? And this is going to be, again, my feedback resistor. So in both of these cases, I know that at just get rid of my highlighting, that at this point, my voltage is going to be equal to V2. And at this point, my voltage is going to equal V1. And I'm going to use that to my advantage here. So I know that this right here is equal to V2. Make that red so you can see it a little better. So I know this is going to be equal to V2. And I know this voltage right here is going to be equal to V1. And again, that's because we have feedback, right? And we know that, that this voltage right here, when we come around here, that's equal to V1 because they have to match. And this voltage right here has to equal V2 because they have to match. Okay, so what that does is that allows me to find the current through RG. And once I can find the current through RG, then I know the current through R here, and I know the current through R here. And what that is great for is if I know this voltage at V2, and I know the current through this resistor right here, then I can figure out the voltage here. And the same thing, if I know this voltage, V1, then I know the current through this R, then I can find the voltage at this point right there too. So that's what I'm going to do. Let's get rid of some of my highlighting there. Okay, so I'm going to find, we'll call this IG for now. The current through RG. So we're going to say IG is going to equal the voltage drop. And we know the voltage drop. If we look back up here and we look at this V2, right? Our V2 is 4.2 and our V1 is 1.9. And so that tells me that V2 is greater than V1. So if that's the case, then I know that my current is going to be, so this is going to be equal to 4.2. And this is equal to 1.9. So that must mean my current is flowing this way. So that's going to be my IG. So IG is equal to V2 minus V1 over RG. And that's equal to 4.2 minus 1.9 volts over RG is 2K, I think, 3K. And so that current then is 0.77 milliamps. Okay, great. So that's my current. And so remember that if my current is flowing up, then that must mean that my voltage here at the output of this V2 op amp is going to be greater, right? If I have current flowing this way, then I know that my voltage here has to be bigger than my voltage at V2. So I'm going to find this voltage, and I'm going to call it let's call it V2 out here, V2 out. So I know my current's going this way, so I know V2 out has to be bigger than V2. So what I'm going to do then is I'm going to say V2 out, oops, I'll go back to black, there we go. So V2 out is equal to V2 plus IG times R. And remember, I need that to be bigger, right? V2 out has to be bigger because of the direction. There needs to be a voltage drop from V2 out to V2, so it's got to be bigger. So that's going to be 4.2 volts times, or plus 0.77 milliamps times R, which is 6K. And so that V2 out then is going to be equal to 8.8 volts. Great, and now I can figure out my V1 out. So again, this is going to be over here. This is going to be my V1 out, and I'm going to use the same procedure. So what I'm going to do is I know that since the current is flowing this way through R, I know that the voltage at V1 out has to be less than the voltage at V1 because of the direction of current flow. So I'm going to go calculate V1 out. So V1 out is going to equal V1 minus IG times R. So that's going to be equal to 1.9 volts minus 0.77 milliamps times 6K. And that's going to give me a negative 2.7 volts. So there it is. I have my voltages at those spots. And so what I want to do first is I'm going to start with this leg right here. So if I know V2 out, right, and I know it's connected to ground, I can use, I can say V2 out minus 0 divided by this R plus this R. So I'm finding the current by taking this voltage divided by 2R. So let's do that. So we're going to say, I'm going to call this, let's see, I'm going to call this current is going to be I plus. And I don't have any current here, remember, because the I is equal to 0 into the op amp. So I don't have to worry about that. I just have all my current in this I plus leg here. So I plus is going to be V2 out minus 0 divided by 2R. And that's going to equal, V2 out is 8.8 K divided by, really just divided by 2. Well, actually, let's go back for a second. Let's do, instead of doing I plus first, let's just do the voltage across each one of these resistors, because that's kind of easy on the bottom. So we're going to do, for the bottom, or the positive, so the bottom leg, I guess, we'll say that V of R is equal to V2 out minus 0 divided by 2. It's split, right? So if I have this V2 out, and I'm saying that divided by this resistor plus this resistor, since the resistances are the same, I can just say V2 out divided by 2. I drop half of the voltage across here and half of the voltage across there. Okay, so that's going to equal, equal 4.4 volts, right? Because V2 out is equal to 8.8. Okay, so now let's say I plus is going to equal V2 V2 out divided by 2R, which is equal to 8, so minus 0. 8.8 volts divided by 2 times 6K, and that's going to equal 0.73 milliamps. So what I'm trying to do now is I'm trying to find, so I've got my current there and I've got my voltage drops, and I also need to know the voltage at this point right here. And because I know the voltage drop across this resistor, I know this voltage. It's got, this voltage is what's left to drop across this R resistor here. So we know that that is 4.4 volts. So this V, we call this, I'm going to call this is our V plus, right? The same as our V plus in here. So V plus is equal to 4.4 volts. And what we like about that is because we have negative feedback, we also know that this V minus, so V minus is equal to 4.4 volts. And if that's true, then this spot right here, this V minus is equal to 4.4 volts. V minus equals. Okay, so so that's great. So we'll have V plus is equal to V across R, which is equal to 4.4 volts. And that's also equal to V minus. So now we can find I minus, because if we know the voltage at V minus here, and we know this voltage V1 out here, then we can find the voltage drop across this R and then find the current. So let's find the voltage drop across that R first. So we're going to say the top. Let's do this first. We'll say on the top, the voltage drop across R is going to equal V1 out minus minus V minus. And let's look and see what the direction is. So we know that V1 out here is negative 2.7. So this is negative 2.7 and this is 4.4. So that tells me that our current is actually flowing this way. So this is going to be my I minus. This is my I minus. So let's instead then write Let's erase this and we'll say we're going to do, since we want it, we'll keep it positive, V minus minus V1 out over R. And so that's going to equal 4.4 volts minus a negative 2.7 volts over 6K. And that is equal to, or sorry, that is, let me go back and do, I'm getting ahead of myself here. I just want the voltage drop first. So I want V minus minus V1 out, and that's equal to 4.4 volts minus a negative 2.7 volts, and that is equal to, where did I write that down, 7.1 volts. Okay, and then I minus is going to equal VR over R, so 7.1 volts divided by 6K, and that's going to equal 1.18 milliamps. Okay, so now that we know the current here, so we know the current here, which means we know the current here. So, and we know that the current is flowing to the left, and so that means that we know we have to add IR, so this IR to 4.4, because we know that V out is at a higher voltage than my V minus. So what we're going to do is we're going to say V, and we also know VR is equal to 7.1, so really V out is going to equal V of 1 out plus V across R, because that voltage drop across the R is the same, right? The voltage drop across this R and this R are equal. Oops, I want to do that. All right, so that's going to equal negative, or actually that's not quite right, is it? We want to be minus here. So we want V minus plus V sub R, so that's going to be 4.4 volts plus 7.1 volts, which is going to be equal to 11.5 volts. So that's our V out, and that's exactly what we calculated over here. So that matches. And have we forgotten anything? I think we've calculated all of the currents, and we've calculated all of the voltage drops. So I think that is everything for that problem.